Well, hello everyone, I'm Josh. I'm a maintainer of the Dapr project, but I'm going to talk about some of the workflow and actor improvements we made in the 1.16 release, particularly around performance and resource usage. So if you're not sure about workflows, so workflows is a engine in Dapr which allows you to define kind of deterministic and durable execution of business logic. It can take different paths based on inputs and outputs, and ensures that that workflow durably executes until the end, or errors or whatever else. But yeah, if your kind of machine blows up from a meteor or something like this, then that workload will be scheduled on another node somewhere in your cluster, and then continue executing. So that's what a flow engine does. Again, to go through very quickly, obviously we're in Dapr, so you define your workflow in the programming language of your choice. But of course, now with multi-application workflows, you can now do it in multiple languages and do it that way as well. We support things like fan out, fan in, external events, timers, child workflows, things like this. But going on to, so now I want to talk about an important note about how workflows implemented Dapr. So in Dapr, we have the concept of actors, which is a building block inside of Dapr. And actors are a programming paradigm where you can define a single-threaded execution of a particular process, and you can have lots of them, and they can talk to each other. You can kind of read more in the documentation about the actor model. But it's important to note that the workflow engine is built atop of the actor model, and this is done for a number of reasons. So in the actor runtime, we have the concept of this turn-based single execution of an actor. So a particular actor ID can only be executed once at a time in a particular place. And that is very useful in the context of the workflow engine, because when you have a activity that you want to run, you want to ensure that that activity is only run on a particular host at a particular time and not multiple places. Of course, you can be using a workflow engine for critical systems such as payment processing and things like this, and you definitely don't want to be paid twice or send money twice, things like this. So the actor model is useful for this. Also, it's useful for workload balancing. The concept in Dapr of actor placement. So we use the placement service to distribute actor IDs over a natural distribution across all of the replicas. And so with using the workflow engine on top of actors, we get a natural distribution of the workflow execution across all the replicas for a particular workflow. And then finally, identity-based isolation. So workflows have identity, they have a name associated with them, as well as an instance ID and an execution ID, and each of the activities are named and have these IDs, and these all get fed into the actor system, where we have an actor ID that represents all of these instance IDs and so on. And it's important to kind of bring this up, because a lot of the performance improvements that we made to the workflow engine also kind of tie into the actor subsystem as well. Great, so we made workflows stable, and that was great. But in this release, we focused a lot on the performance improvement. So I'm going to go a little bit into the kind of nitty-gritty details here, which might be interesting for you. And obviously, Dapr, the runtime is written in Go, so these are kind of a lot of these are kind of Go-specific things, but kind of generally kind of software engineering kind of stuff as well. So a lot of the things we made changes to was reducing memory allocation, so reusing data structures across and reusing those data structures across different actors. In Go, we have this kind of nice utility called sync.Pool, which allows you to, once you're finished with a data structure that you don't need to use anymore, you can give it to this kind of pool of data structures of same or different types, and that you can pull from that pool at a later time without having to go back to the operating system and say, give me more memory. We can reuse that memory. So we reduced allocations, we re-architected a lot of the actor runtime to reduce those allocations generally. So moving a lot of the shared memory kind of further up into the system, which reduced things a lot. We reduced contentions. So specifically, when I talk about contentions, that is where it goes back to the kind of turn-based actor kind of behavior I was talking about before, whereby instead of getting to a particular stop in the code and then having to wait to get to your turn, we've re-architected things so it reduces all of those contentions. So removing things like mutexes in favor of just kind of continuing on, and then also having a concept of this kind of optimistic getting of memory. So instead of having mutexes around maps and things like this, we use called a sync.Map, which optimistically tries to write or read from that map, and then if it didn't win, then backing off, as it were. So kind of reduces the amount of time that the program will be kind of locked and waiting, which is useful to kind of keep things going, and also reducing context switching and things like this, which can lead to performance degradation. We reduced a lot of the Go routines that are used as well throughout the runtime in favor of using callbacks. This is helpful as well because this means that although Go has a very great system with Go routines, and the kind of orchestrator for the Go routine runtime inside of Go is very good. Once you get up to something like 1 million Go routines at the same time, the performance degradation kind of isn't worth the benefit, right? Like, it doesn't really make sense to have many Go routines. So we've removed a lot of those as well, and we've also made some changes to the way that the Dapr talks to the scheduler service. We have more streams open now, which helps with bursting and kind of general throughput and things like this. So a lot of kind of smaller kind of nitty-gritty details, but once you kind of start adding them all together, you see this kind of a much better performance numbers generally, but also a better performance profile, which I'll move on to now. So, for example, this is running, these next two slides are running for on an EKS cluster. So we're running a 3-node EKS cluster with T2 medium-sized nodes, I believe, and they will be running 3 replicas, and we're executing 1,000 workflows with I believe it was 15 activities that are kind of doing the kind of operations. The main thing is running workflows with those activities, and then we're scheduling all at the same time and then waiting for them to finish. The top one is 115 and the bottom one is 116, and you can see here with the memory difference, you can see that the 116 has by definition uses less memory. You can see it peaks at the top here at 130 across the 3 replicas, and at the bottom one they all peak at 90. What's also important to note is that they peak at the same place, which means that we have a much better memory distribution across our replicas. So we're using close to the amount of same memory, which is a good performance profile to have. This helps with replica bucketing. Also, they are a lot more stable. And this is much better for designing how much memory you're going to need. So capacity planning is much better when you have a kind of stable profile like this. So we have a much more memory profile stable system, and it is a lot more consistent across the replicas. So we're doing much better at utilizing all of the kind of resources across the replicas in the same amount of way. And we go on to CPU, and it's much the same story here. We're using less CPU by default. You can see here it kind of peaks out at 0.08, and before it's 0.25, so we're doing a lot better here. And again, it's consistent and they're much closer together, which is much better for kind of bucketing and capacity planning scenario. And then finally, there's a big graph here showing different scenarios. Less is better, and you can see blue is across the board lower. And as you can imagine, as we're going to get further up in scale with the number of workflows running at the same time or replicas, you can see the bigger difference in the performance improvements we've made. You can see here that some of the orange bars aren't even present on this graph because the system just conked out and can handle it and crashed out. So we're doing a lot better now with stability with these kind of larger kind of workflow throughput scenarios, which is great. Also, a big takeaway, the main takeaways, we got less resource consumption across the board. That resource consumption is much more stable, particularly at scale, and we've reduced the workflow time to completion. So specifically going back to this graph, this is time to completion of the workflows, and I've got some links there as well. You can look at the release notes that we had for 116, which goes into this with more detail, and yeah, the workflow overview documentation I've added there as well to give yourself a bit of a read on workflows generally. With that, I will hand it back.
Thanks a lot, Josh. Great to see all these detailed diagrams. Cool.